Alright, so I have a quiz from 2011 that has some of the material we've been talking about here. In particular, the quiz is focused on polar coordinates and parametrizations and so forth. So here I gave the description -1 less than r less than 1 and 0 to pi over 3. So 0 to pi over 3 is this, and if we just had 0 less than, if we had just 0 less than r less than 1, it would just be this, right? But since we also allow 0 to -1, that flips us over to here for the negative r's. Next question was convert tangent theta to 1 in Cartesian coordinates, identify the curve. So sine theta over cosine theta is 1, which gives us that, which gives us y equals x. It's a line. Now, I guess that's okay, but to be fussy, you know, I definitely am missing the origin, you know, so some people might say it's not really a line, it's a line with the origin punctured. And I'd be like, oh, well, good, you're being more careful than I am, it's not bad. Next I've got r equals to 2 sine theta, I multiply by r, I complete the square, I get x plus y minus 1 squared equal to 1, alright? Next I say find the polar radius and standard angle for the point -2, 3. So r is simple enough, square root of x squared plus y squared gives me square root of 13. And this time I take inverse tangent of y over x, which is 3 over 2. But I have to add pi in order to get into the proper range, which should be somewhere between 180 and 270 degrees, or pi and 3 pi over 2 radians, which I do indeed have. Draw a picture to be sure this point is in quadrant 1, 2, 3, so we definitely should have that kind of standard angle. Alright. Next up here, I am asked to eliminate the parameter t to find the corresponding Cartesian equation for the curve described parametrically below, and also to give inequalities for x and y, if as necessary to explain. So here, I give them a parametrization of a line segment actually, which I plot down here. Plug in 0, you get 1, 2. Plug in 2, you get 1 plus 6, which is 7, and 0, so we get 7, 0 is the end point. And so of course you could also look at this in terms of vectors and see directly that the base point is 1, 2, and the direction vector is 3, minus 1. Anyway, however you do it, you can then find the equation of a line connecting these 2 points using whatever you like in terms of how you think about lines. But I chose to eliminate time by solving for time, and that gave me x minus 1 over 3 is equal to 2 minus y, which then I solve for y. And there you go, that's the equation of the line. And you can see it from here that 1 is less than or equal to x is less than or equal to 7, and 0 is less than or equal to y is less than or equal to 2. These are inequalities that hold for x and y here. Sorry, I think I might have been off the edge of the paper there. There it is. Of course, these are posted on the resource page in case I'm ever off my, in case you ever can't see something that I'm talking about. Now this is a shifted circle. Oh, wait a minute, no, this is an ellipse because I have a different multiplier here and there. So this is going to be an ellipse. The key is that cosine squared plus sine squared is 1, and that gets me to here, which shows me that's in fact an ellipse. But it's not a full ellipse because we only go from 0 to pi, which means that we're only swinging through that much. If you think through it, t equal to 0 gives me 3 and minus 2. And, oh, excuse me, 3 and 0, which is this point. 0, comma 3 to be more proper, right? X then y. So plug in t equals 0, I get minus 1 plus 1, which is 0, and 3 plus 2, rather 3 plus 2 times 0, which is 3. So I start there. When I get to pi, I've gone all the way over to minus 2 for x and still 3 for y. So I'm swinging like that. So there it is. So, you know, if I do ask you to plot something for a parametric curve, it's probably going to be a line segment or an ellipse or a circle or a hyperbola most likely. So next up here, I asked the class to plot the parametrized curve here, which was x equals sinh, y equals 2 cosh, which is, again, going to be a hyperbola as it happens here. And you can see what happens. Essentially ignoring the 1 if x and y are large, we have y is asymptotically plus or minus 2x, which helps me make a nice picture. And the hyperbola, a Cartesian equation's that. And this 2 cosh is a dead giveaway. This is going to have, so x equals sinh t is not bounded. Sinh takes on all values. This means that t is a real number. So sinh of a real number could be anything, but cosh of a real number is larger than or equal to 1. So this means that y is greater than or equal to 2. I can see that from this formula. All right. Next up, I asked the students to show on this quiz that the circumference of a circle is precisely 2 pi r. And so to do that, they needed to parametrize the circle, calculate the arc length, and integrate, just like I showed you in a previous video. All right. Next up, so I don't know if there's any problems quite like this in your homework, but if you were given the velocity, you could integrate to find the position, and you could differentiate to find the acceleration. So this is a nice problem, you know, because it involves both differentiation and integration of a vector. But probably this gets covered in your Calculus 3 class. I don't think I covered in Calculus 2 on the line. Residentially, though, I might cover it. Let's see here. Find the parametric equations for a line which goes from 1, 2 to 419, either in scalar equations or as a vector equation. So standard vector trick, base point plus t times, the line q minus p vector, which gives me this. These angle brackets, don't be distracted by them. That just emphasizes it's a vector. So we either have that as the vector formulation, or x equals that, y equals that as the scalar parametric equations. And there you go. Let's see, r being a positive constant, x equals r cosine, y equals r sine, with t ranging between plus or minus pi over 2. And then rotate this thing around c. Just set up the integral, don't finish the calculation. Well, that was kind of silly. We could definitely have finished the calculation. It's just the yet another setup for the surface area of the sphere, right? All right. All right. But the larger point is that the dA is 2 pi r ds. Here ds we can get from x dot squared plus y. This notation means dx dt and dy dt. That's what dot means, all right? So anyway, I think that may have already been tested, but to calculate the work done by a variable force, we integrate the force. Yeah. Let's see here. And now here's a graphing. I have given r equals 1 plus theta over 2 for 0 less than theta less than 6 pi. And I say I want you to graph the r theta plane and then use that to create the xy plot. And so here's an attempt at a good graph. It's kind of okay, but so of course 1 plus theta over 2 is just a line segment, since it only ranges from 0 to 6 pi, and then that gives me these spirals. All right. 10. Find the equation for the tangent line at 1, 1 with parametric equations x equals cosh t plus t and y equals t squared plus 1. So you notice that 1 equals to t squared plus 1 tells me t equal to 0 at the point of tangency. And then you can check t equals 0, cosh of 0 plus 0 is 1. Yeah, okay, that makes sense. And so there's our position, there's the velocity differentiating. And then when we plug in time 0, of course, we get 1, 1. When we plug in time 0 into this, we get 1, comma 0. So the parameterization of the tangent line would be 1, 1 plus t times 1, 0. This is the vector parametric equation of the tangent line. Excuse me. Now, to find vertical tangents, we look for where dx dt is equal to 0, which in this case gives me sinh t plus 1 equal to 0, and I get inverse hyperbolic sine of minus 1 is where there's a vertical tangent. And you can notice that dy dt is 2t, and it's not equal to 0 at that point. To be careful, I really should check that dy dt is non-zero at the place where dx dt is 0 to be sure it's a vertical tangent and not something weirder. But there you go, there's one vertical tangent to find. 11, suppose C is a curve, which is the solution set of that. Find a function f such that the inverse image of 4 gives this curve C. Alright, so there are various options, but what I chose to do was to put a 4 over here and subtract 30 to the other side. I called this thing f of xy, and there it is. There's really not much to this problem. It's just a question about, do you understand what I said when I said a level function? And there's not really much to understand there, except that f of xy is a notation to capture some expression, which then, when equal to a constant, defines a curve. Or to be more specific, the solution set to that equation defines the curve. And then here, the question is it possible to find a function such that the graph of f is equal to c? And the answer is no, because it would fail the vertical line test for reasons that are described there. Man, this is a long quiz. Let's see here. That's usually what I do, though. I give a quiz which is too long to try to get the students up to speed for the test, which soon follows thereafter. Find the area bounded by r equals sine theta. That's actually a circle of radius 1/2 centered at 0, 1/2. So you could calculate the area is pi over 4 directly, or you could do the integration to figure out it's pi over 4. And then problem 14, I asked the students to derive a formula for d squared y dx squared in terms of time. And if you work it out symbolically, you can get that y double dot times x dot minus y dot x double dot divided by x dot cubed is a formula for the second derivative. Now, we didn't actually use that. We actually just differentiated dy dx in our previous work, but this is another sometimes useful formula to know about. All right, that brings us to our next old test, which was test 2 of spring 11. And I won't go through all the details, just kind of talk loosely about it. Problem 1 was to find the parametrization for a line segment. Problem 2, I asked them to basically give a function that the given solution becomes the level curve of. So basically, this is to describe a curve implicitly by the way I've set it up. Really not much to say about problem 2. Problem 3, I wanted them to find a counterclockwise parametrization of the circle, which has y greater than or equal to x, and here's a plot of it. All right. So, you know, plotting and thinking through is so important for these basic circles and angles and so forth. Here I gave them the Cartesian equations for a hyperbola, a hyperbola, and I wanted them to sketch it, so they sketched it and found the Cartesian equation of the hyperbola, again based on cos squared minus sin squared being 1. Here I gave actually a vector form of the parametrization, x equals to that, y equals to that. I said find horizontal and vertical tangents, so we looked for where dy dt was 0, and we looked for where dx dt was 0, and fortunately they're not 0 together, so nothing weird happens. These are genuine horizontal, and these are, you know, genuine vertical tangents at those times. Now, to actually find the equations for the tangents, I have to take these values for t and plug them back into the respective formulas for x. The horizontal tangents, for example, I would take and plug these times into the y, which give me y equals to whatever it is, and y equals to whatever it is at those values. And let's see here, the vertical tangent, I put, you know, that into here, and I would get x equals to 0 as a vertical tangent, all right? And then I asked to find the integral representation for the arc length. Do not calculate the integral. If I say do not calculate the integral, I mean it. do not try to calculate this integral, but that integral would describe the arc length. All right. Now, here's again that problem I sometimes like to assign where I give the velocity and say define the acceleration and the position, which comes from integrating and differentiating appropriately. But anyway. And here, find the arc length of this curve. So it's a pretty standard problem. You got to calculate dx dt, calculate dy dt, add the squares of them, simplify, things cancel, and you just get something relatively nice, which then you can integrate to get that. Not that bad, actually. It just looks kind of scary. Although if you don't know how to differentiate 3 to the t, you'll be in trouble, right? The derivative of 3 to the t is log 3 times 3 to the t. Problem 8, find the surface area for this thing. And look at the surface area of the sphere again. I am a creature of habit, aren't I? Let's see here. Then find the polar form of this equation. So we got to put in our cosine theta and our sine theta for x and y. Tangent of y over x, well that's tangent of tangent theta. That's kind of funny. And didn't say it'd be pretty, but there it is. And the Cartesian form of this equation, that's 3x equals to the square root of x squared plus y squared. So you could, there, it's that, or you could square both sides and get that. Interestingly, this is actually y is just equal to plus or minus 4x. Do I believe that? No, I don't believe that. Is the square root of 8 4? No. Come on, people. I mean, come on, me. All right. This correction probably just for you guys here. Actually, interestingly enough, that's actually a pair of lines, it looks like. Cool. These lines are probably where 3 cosine theta is equal to 1. So cosine theta is equal to 1/3, which would be, well, anyway. Apparently along the lines y equals plus or minus square root of 8 times x. Let's see here. Next up, I wanted them to plot the polar curve r equals to sine 3 theta. Now we've looked at sine 2 theta in previous video. Notice that something interesting happens. 3 theta does not give me 6 petals. It just gives me 3 as it happens, as you work it out. And so like from 0 to pi over 3, we get this, I'll do some, basically this piece right here gives us this loop. And then from pi over 3 to 2 pi over 3, we have a negative. Pi over 3 to 2 pi over 3 of a negative, which is giving us this loop down here. And then from 2 pi over 3 to pi, we got that, which is giving me, let's see, what did I just say? From 2 pi over 3 to pi, which would be here. We get that. And then as you go on, you just retrace your steps. So it's just that. And then to calculate the area enclosed by the curve, which is actually kind of a nice question, just pick any petal you like and multiply by 3. So I decided to use the first petal, which goes from 0 to pi over 3. Inner radius is 0, outer radius is sine 3 theta, so 1/2 r squared d theta squared, which gives me this. By the way, integrating cosine 6 theta goes to 0 because that has a period of pi over 3, I think. When 6 theta equals to 2 pi, we've gotten a full cycle, so 6 theta equal to 2 pi is, theta is 2 pi over 6, which is pi over 3. Yeah, so we're integrating this over a full cycle, so that just integrates to 0, and we just get that, pi over 4. And then this one's kind of interesting. Find the equation of the tangent line to the curve, r squared minus 3r plus 2 equal to 0 at the point 2, 0. So if you're not thinking and you're just a slave to formulas, you'll be in trouble here. But if you factor this, you've got r equals to r minus 1 times r minus 2 equal to 0, which gives us r equals to 1 or r equals to 2. It's a pair of, this is actually a pair of concentric circles about the origin. And so it's really, you don't need equations or anything fancy. When you want to find the equation to the tangent line at 2, 0, you look at it, you go, oh, it's vertical. It's just x equals to 2, right? So there's no, you know, fancier stuff going on there. You just got to be geometric. And, oh, we calculated this not long ago, the arc length of, whoa. What? Uh-oh. I think I made a mistake in a previous video. Huh. That's funny. Oh, you know what I think? When I did this before, I didn't square the theta squared. Oopsie. Well, I'll have to put a note on that one. I don't remember where that was. So apparently, it's much uglier. Yeah, so apparently if you integrate the, if you find the arc length of the polar spiral theta squared between 0 and 4 pi, it is not so nice. It actually works out like this. Well, like this. And then, well, that's a U substitution. It's not too bad. Like this. And I got that. But that is not as simple as what I had previously. Sorry about that, folks. Here's a problem about the force of water on the end of a pool. You know, this is a let's see here how to say this. So the issue with this is the force depends on the depth, and so the little bit of, oh no, I'm calculating the work. What am I doing? Oh, work done to pump the water to the surface. Goodness, I don't think I have any homework like that for you guys at the moment. Now, problem 15 is we've done something like that before. I mean, problem 14 is a nice problem for physics, but you know, set up an integral for the hydrostatic force on the dam pictured below. So dA is W dy, which would be F of y dy. Pressure is rho gy, which is dF dA. So to calculate dF, I take rho gy dA. But here dA is F of y dy, so I would integrate from 0 to h the density times g times y times F of y dy. And I told up here that the width was F of y. That's where that's coming from. All right, enough about that. And then finally, this is a challenging calculate the area of the intersection of the areas bounded by these three things. So inside these, and so you could debate. Well, I think it was clear that that's the place which is inside all three. And if you look at that, it's itself divided up into 3 pieces. See, because if you look at it more carefully, you've got this sliver, you've got that sliver, you got that sliver, you got case 1, 2, 3, and you have to, yeah, a little bit fussy. Anyway, I hope that gives you a sense of the kind of problems that we like to ask about parametrized and polar coordinates. Parametric equations play a major role in Calculus 3, so it's important to get started on it. We are by no means finished with that topic in calculus. We have much more to say about it in Calculus 3, and similar things apply to polar coordinates. So anyway, next up for us is differential equations. So thanks.